Okay, let's take a look to these constitutive electrical parameters of the transmission line. We have been talking about inductance, capacitance, the resistance of the conductors, the conductance of the dielectric. How are these parameters determined? Well, here these parameters actually depends on the capacity of storing magnetic or electric field energy of the line, and also the losses mechanisms related to the resistance of the conductor and the conductance of the dielectric are related to the losses mechanisms. And this can be calculated from the description of the magnetic or electric fields around the conductors in the line. So you see here, for example, a cut, a transversal cut of a two-wire line. You have here the two conductors and the dielectric in this case. You have here in the solid line a description of the electric field lines. The H magnetic field is described by the dashed line here. So if you have a good knowledge of this, then you can just, by these integrals, calculate what is the energy stored in the magnetic electric field and so forth. And in this way you can calculate these LC and RG parameters. For the losses parameters, you have to know what is the surface resistance of the conductors. This is this RS parameter here, or what are the loss factor of your dielectric, which is actually described by this permittivity here, this imaginary part of the dielectric permittivity of your dielectric. So this is how these parameters are calculated. What you see here in this line are some representative examples of typical transmission lines. You have, for example, in the center, the two-wire lines that we have been talking about. You have here the expressions for these LC, RG parameters, and the same happens for the coaxial line here in the left, or the parallel plate line, which is actually similar to two-wire lines, but in this case the two conductors are just two parallel strips which are separated by a dielectric with a distance d. So you have here the parameters in these in different transmission lines, and you can actually, if you use a different line, you can always, if you have a description of the fields, you can always compute what are these constitutive parameters. What is the usage of the different transmission lines? Well, it depends very much on the application. So, for example, for radio frequency devices, communications, high-speed communications, what we use in many cases is the microstrip line, because it's very popular for the simplicity of fabrication. It is just you can just make these lines like a PCB with etching fabrication. And what is the line actually? Well, the line is actually a modification, if you want, of the two parallel plate lines, which is here in the left. Then if you take, if you eliminate, for example, one side of this line, and you substitute it by a ground plane, which is just a metallization which is grounded below the printed circuit, then the active element which remains have an image here which reproduce what you have here in the two parallel plate case. So this microstrip line, which is just a printed line, you have here, for example, the input and the output of an amplifier, and actually this central strip here is the active element of the microstrip. You have here a grounded mass plane here around, and also below you have a complete solid plate like this shows in these schematics here. Actually, this line is a transmission line, has a defined impedance which actually is the half of the impedance of the two parallel plate lines which you have here in the left. So this is a very typical transmission line in radio frequency and very high speed applications. And for the microstrip, actually the accurate modeling of the microstrip is quite complicated because we have two dielectrics involved. We have air above the strip and we have a solid dielectric below. So actually, instead of permittivity of only one dielectric, we have two dielectrics involved, and that's the reason why we have to use an effective permittivity here, which can be calculated from these expressions, and also the impedance here can be calculated from these expressions. So it's a bit complicated, but it can be solved, and these expressions are known. And you can calculate the parameters of your microstrip line from this expression here. If your line supports very high frequency, you have to take into account, or your line is very long, you have to take into account the losses, and then the attenuation of the microstrip can be calculated from these expressions here, and this attenuation is in Nepers per meter. We will talk of this in a future lesson. And the parameters involved for the losses are the surface resistance of the conductor, of the strip, and also the dielectric loss, which is modeled in this case with a tangent delta parameter, which depends on the imaginary and real part of the permittivity. Let's take a look at an example of a usage of microstrip lines in this case, for a radar system. What you have here in this box is a radar, is a low power radar, is a continuous wave FM radar. But what is interesting for us is we have here amplifiers, filters, mixers, more filters here, again amplifiers. What is important here is let's take a look on the connectivity of all these elements, or all these subsystems. You have here, for example, a very long transmission line, which is actually relating the signals in the transmission side, which is this upper side of the radar, and this is the reception side of the radar. So you have here transmission lines everywhere, and they are also used here for this. These are actually devices are filters, and these filters are made with pieces of transmission lines again. So they are used for many connectivity situations, and also as part of subsystems like filters, power dividers, and so on. So they are used very much in microwave circuitry.